Hello everyone, so today we're going to go over section 3.12, linear approximations and differentials. Linear approximations are used to approximate the value of a function at some x value using the tangent line as an approximation for the value. The values that we're looking for will be relatively close to known values of the function. The goal of linearization is to approximate a curve with a straight line, more specifically the tangent line. And the reason why we want to do this is because it's much easier to find the values on a line compared to a curve. So for example, suppose I have a curve here, y equals f of x. Okay. Here we have an x value of a and a y value of f of a. Okay. So this point here will be a f of a. You can see here we have drawn a tangent line at x equals a. We'll call that y equals L of x. Recall that the format for tangent line would be y minus y1 is equal to m and then x minus x1. For the tangent line, we know this will be y minus f of a and then f prime of a multiplied by x minus a. If we are to rearrange this slightly, we'll have y equals f of a plus f prime of a x minus a. And that will be the equation of L of x. Oops, sorry. So instead of the value a, we tend to use x naught instead. So a will be equal to x naught for the purpose of linear approximation. We use linear approximation to find the approximate value of f of x1, and x naught will be given to us, or we can find it pretty easily. Usually it's a value, it is associated with a value of the function that's already known. Now, of course, if we simply substitute x1 into the function, we could find the value, but usually, oftentimes we don't know what the exact function is in real life, so we cannot necessarily do that. Okay, and here it says the differential dy is defined in terms of dx in the equation dy is equal to f prime of x times dx, where dy is dependent variable and dx is the independent variable. Dy represents the amount that the tangent line rises or falls, whereas, of course, delta y is the actual change in y value of the curve. So let's examine this using a diagram. Okay, once again, we have the curve y equals f of x. And then we have the tangent line y equals L of x. And we're given two different x values here. They are going to be x naught and x1. So of course the corresponding y values will be f of x naught and f of x1. Okay, so you can see here we have the change in x value from x naught to x1. That is known as, of course, delta x, which is equal to dx for our purposes. The change in y value here on the curve, that is a delta y. Whereas the change in the y value from the tangent line to where x L of x1 is this line right here. This would be dy. Okay. So the idea is this: dy dx is equal to f prime of x. So dy is equal to f prime of x times dx, if you multiply both sides by dx. When delta x is small, then we can approximate that delta y is close to dy. Okay, so that means delta y would be approximately equal to f prime of x times dx. Delta y, of course, will be f of x1 minus f of x naught. And that will be, once again, approximately equal to f prime of x naught. That's where the tangent line originates from. And then x1 minus x naught. So if we are to use the linearization to approximate the value of f of x1, we will find that f of x1 is approximately equal to f of x naught plus f prime of x naught, and then multiply by x1 minus x naught. Okay, so that will be the linear approximation equation that we'll be using right here. And of course, this substitution was possible because we made the assumption that dx is equal to delta x, as stated on the graph on the left. Again, this is closely associated with the equation of the tangent line, which once again, if we specified it at L of x1, then that will be equal to f of x naught plus f prime of x naught, and then x1 minus x naught. So the idea here is that f of x1 can be approximated with L of x1, where f is the function and L is the tangent line respectively. So let's look at some examples. Okay, suppose we have the curve y equals to the square root of x right here. Square root of x. And these two given x values are 4 and 3.8 respectively. So of course the square root of 4 is 2, but we're trying to find out what this is using a linear approximation. Okay, let's write down the linear approximation formula, if you will. And that is f of x1 is approximately equal to f of x naught plus f prime of x naught, and then x1 minus x naught. Okay, so in this example here, f of x, of course, is the square root of x. If we take the derivative, f prime of x would then be 1 over 2 times the square root of x. X naught in this case is 4, and x1 is 3.8. So we can substitute each part into the linear approximation equation. We will have the square root of 3.8 is approximately equal to the square root of 4 plus 1 over 2 times the square root of 4, and then 3.8 minus 4. So here we can evaluate. Square root of 4 is 2. Again, square root of 4 is 2, multiplied by 2 is 4 here. and then 0.8 minus 4 is negative 0.2. If we convert everything into fractions and multiply these together, we'll actually get 2 minus 1 over 20, which will result in 39 over 20, which is 1.95. So in other words, the approximate value of square root of 3.8 that we'll get using a linear approximation at 4 will be 1.95. Okay? Which, if you use a calculator to find out the square root of 3.8, it is actually very close to 1.95. So this is a good approximation. Let's move on to another example here. It's very similar. Once again, we are going to list out the elements that we know. We know that our function this time, once again, is going to be square root function because we're looking for the square root of 51. So we will have the same derivative. Once again, f prime is going to be equal to 1 over 2 times the square root of x. X naught, we're going to find a square root that's close to 51 that's easy to evaluate. So 49 would be quite good. And x1, of course, is 51. And once again, we're going to apply our formula here. So this will be f of x1 is approximately equal to f of x naught plus f prime of x naught, and then x1 minus x naught. Okay, so we're going to go ahead and substitute once again. We will have the square root of 51 this time is approximately equal to the square root of 49 plus 1 over 2 times the square root of 49. And then, of course, in parentheses, 51 minus 49. So, if you evaluate the square roots, that will be 7. And then 2 times 7 is 14. And then 51 minus 49 is simply 2. So really, this simplifies to 7 plus 1 over 7. And if you use a calculator to evaluate this, this is approximately equal to 7.1428 and so forth. And the actual value of the square root of 51 is very close. It will be 7.1414 and so forth. So a good approximation once again, as you might expect. Okay. Of course, you can also use linear approximation for functions that are not the square root function. Let's look at example 3 together. It says approximated value of cosine 32 degrees. Okay, once again, we have then, well, our function will be simply cosine of x. Its derivative will be negative sine x. X naught, we're looking for an angle that has a nice cosine value, so that would be 30 degrees. And x1 is going to be 32 degrees. Okay, once again, we have our formula. So f of x1 is approximately equal to f of x naught plus f prime of x naught, and then x1 minus x naught. So in this case, this would be cosine of 30 degrees minus sine 30 degrees, and then 32 degrees minus 30 degrees. Okay, so cosine of 30 degrees is the square root of 3 over 2. Sine of 30 degrees is 1/2. And of course, the difference in the angles is 2 degrees. So really, this is just going to be root 3 over 2 minus 1 degree. However, this is very difficult to subtract, so we're going to convert the degrees to radians using the fact that we can multiply by pi and divide it by 180 degrees to change the angle measure in degrees to radian. So once we've done that, we have root 3 over 2 minus pi over 180 degrees. And if you use a calculator to evaluate this, you'll get an approximate value of 0.84857. And the actual value of cosine of 32 degrees would be 0.84805. So again, a very good approximation. Okay, so that concludes part 1 of using linear approximation and differentials. That's it for today. Thank you for listening.